turning the new product. Okay. Only cellulose nanoparticle. Then I said that secretion process, cellulose, nanofiber secretion process may affect to secretion of the new product which can be synthesized inside of the bacteria. That's what I thought. So I just what you understand? So to have a secretion state, you have to have two ways: biosynthesis and secretion. Two processes get together to have a outside product. That's why I just put the synthesis genes, synthetic genes, only genes, no, nothing else. That's why theoretically it's impossible to have bio nanopore outside of the body. But in fact, it was. We successfully produced cellulose with beta-1 secretion outside of the bacteria. Okay. This is a normal culture, like bacterial culture, and this is the product. And we checked, and this service is covered by beta-1 secretions. That's why we conclude that this bacteria, modified bacteria, could produce the cartridge. The general name, cartridge is beta-1 secretions. Beta-1 and beta-1 for nanofiber complex are secreted by gene transformed gene, nucleonas lactobacillus, the name of that bacteria. Okay. Now, well, I don't have to talk about this, but briefly speaking, that template, cellulose template, can be applied for the biomineralization. Because this cellulose template could be a scaffold for inorganic compounds. And also, between the molecule, that's the oriented molecule, because this older cellulose template has some space. That's why we put some ions between the molecule for the ion supply. So we modify the surface like this, because again, the cellulose molecule is well aligned like this, and then we put this kind of phosphorus ions in between the molecule. Then we culture under the calcium-rich solution, and then automatically this kind of ordered structure is formed. And that's the kind of biomineralization process. Okay. And other things, we also try to have a three-dimensional culture of epidermal cells. Epidermal cells is a skin cell. Skin cell. Okay. We put that template at the bottom of this. This is cross-section image. Inside of the container, we put another container. At the bottom, we put that template. In this way, and then outer areas, we put the culture media. And then automatically culture media is passing through from here. And that important thing was that template was half permeable membrane. That's why the current media is coming through this to the bottom. That's why when we put the cells, epidermal cells, skin cells, always new media is coming at the bottom. And then this cell tends to have cell division towards to the bottom. You understand? When you consider the skin, always skin is outer layer skin is old. Inner layer is a new one. That's why the skin division of the cell, in the skin was always from the outside to the inside. Normally, we think that the division is from inside to outside. But the skin's case is different, from outside to inside. So the division direction was different. That's why we use this kind of system to control the cell division direction. Then we culture like this, so we could have three-dimensional layer. So that's successful. This is not so easy to understand and recognize this kind with this not how to say the image, but you can trust me. This is a three-dimensionally established skin-like shape. Okay. Now, thank you for your waiting. Now I'm entering ACC. Now in a three-dimensional structure, I will just introduce a three-dimensional fabrication in our ACC. Once we establish a three-dimensional structure, we need to decompose the product into a smaller scale building blocks by using water. That's why I hit the idea that I don't need to explain this because you may know it. But anyway, we just put the two nozzles facing each other, and we shoot from both sides to a certain characters, and this is not water, it's a water suspension. Suspension means containing a sample. So the containing suspension coming through this and collide each other here, and then automatically it's going down. It's going to be downsized into a small particle. This is a simply a description of the ACC process. But the process itself is so simple, but the phenomena contains a lot of physical, chemical ideas. Okay. Oh yeah. Before explaining the details, this can be applied. Important thing is not only the cellulose, but also we could apply to say collagen. Well, this is not impressive. It's already published. But anyway, this is all slides. I'm sorry. It's published anyway. Collagen, we applied this ACC into the collagen. We could have two kinds of nanofibers. We don't know why, but only two sides. One is 100 nanometer in width. The other one 10 nanometer in width, depending on the pressure. If we increase from 100 megapascal to 150, we could have, yes, 100 nanometer in cellulose, not cellulose, collagen nanofiber. But if we increase from 150 to more than 150 megapascal, we could obtain the collagen nanofibers with 10 nanometer. Okay. Then I didn't have this one, but by measuring the tensile strength, it's about 3 gigapascal. And cellulose is considered as a 6 gigapascal as a tensile strength. That's why even collagen fiber is almost corresponding to the cellulose. I think most people think that the collagen is very weak, right? But in fact, by our experience, the collagen fiber, nanofibers, seems to be very strong. And we apply ACC to chitin in 2010, or the carbon nanotubes 2014. They are all successfully dispersed in water. Okay. without anything. I want to talk about the details, why we can have this kind of situation by using A60. But if I start to talk about this, I have to refer to what is the structure of water with the inside of a chamber or something. It's more detailed. That's why this time I will concentrate on another point of view. Okay. 2 weeks ago.